Hello, everyone. It's my pleasure to introduce our first keynote speaker. He has an exciting lecture to show us today. Dr. Golparvar-Fard is an associate professor, faculty entrepreneurial fellow, and faculty excellence fellow at the University of Illinois at Urbana-Champaign at the Department of Civil and Environmental Engineering. His main areas of research are computer vision and machine learning for monitoring, construction, and operation in the built environment. He's currently an editorial board member of the Journal of Automation and Construction, ASCE Journal of Computing in Civil Engineering, and in the Journal of Construction Engineering and Management. Dr. Professor Golparvar-Fard, the stage is yours.
Thank you very much, Eduardo, for the introduction. Good afternoon, good morning to you all who are joining us on this virtual setting. I'm very pleased to be speaking to you for the next 55 minutes on a journey of research to solutions that I've been working on. I titled my presentation, ABC of Construction, to make it a little bit catchy. But what I really mean by ABC is to speak about how building information modeling that we as a community have been working on for more than 15 years can be integrated with new techniques that are coming out of AI, computer vision, which is the study of images and videos, to generate new types of models that can jointly present as-planned environment with the as-built environment. In more commercial terms, we call them digital twins. And see if we can apply more modern machine learning techniques in the context of artificial intelligence to enable proactive techniques for managing production on our construction sites. So A for artificial intelligence, B for BIM, and C for computer vision. So that's the ABC I have. Before I get into the detail, I want to share with you some statistics. And what I'm going to be presenting to you today is a hybrid of what I do at the university and what I do at my company, Reconstruct, that has brought some of the technologies that I'm going to be speaking about into the practice today. So last few years before COVID-19 hitting construction have been really good years for construction. At least in the US, the value put in place has exceeded 1.4 trillion. In fact, global construction market has also reached a little bit over $10 trillion. But if you look into these numbers and you try to dissect that into various resources and how you're spending our money, you would realize that most recent reports that are coming out from FMI and a few other agencies are showing roughly at a global scale, 40% of our money goes into labor as a resource that we have in the job site. And when it comes to coordinating resources that are needed for our labor, the work that needs to be done by them, there's a huge room for improvement. There are quite a few studies conducted by many of our colleagues who are online today, and some of these publications that are coming out from Forbes and other places that are showing that there's still room for about 35% of the time spent by the labor that can be optimized. So it can be spent on direct work or supporting work that can actually add more value to construction. So if you do the math between the 35%, that 40% that we have on the cost, and escalate that at the scale of what we put in place every year on the job site, you will see the value that can be added in terms of the potential to match our productivity with non-construction industries, roughly close to about $200 billion. That's a really large number. Just to put that into the context, one of the largest stadiums that is currently undergoing construction in the US is roughly around $4 billion, and that's Inglewood Stadium in close to Los Angeles in California. So you can actually have 50 of these new stadiums that can be added if we can actually reach this gap that we see in terms of productivity. Of course, COVID-19 has impacted all of us. This setting is completely online, but this is also impacting our construction projects. Many job sites that we talk to here in the US are implementing social distancing by changing the sequence of the trades that they have on the job site. So we call it white and blue days on the job. And obviously, in terms of days away, restricted, or transferred away from the job site, from a safety and occupational health perspective, is also impacting our productivity. But while you see all these numbers, it would be really nice if you can put them into the context of construction projects. And what that means is impact on the bottom line, schedule and budget. There are a number of reports that have come out over the past few years that shows significant portion of our commercial projects are exhibiting performance that leads into, their project finishing behind the schedule. In fact, a report was published by ENR, Dutch Data and Analytics, in 2016 that shows, more than 53% of our projects in the United States is currently behind the schedule, and roughly a little bit over 60% of them are over budget. Now, when you go beyond commercial projects, and commercial projects ranging somewhere between, let's say, $10 million to roughly around a few $100 million, and you get into the mega projects and anything beyond $500 million, McKinsey shows that 98% of these projects suffer cost overrun, and a large percentage of them are late. That's quite significant in terms of the performance that we have. Now, ironically, if you ask owners across various metrics that we have in construction, what is the one that they care the most about, they would respond back saying a schedule. This is actually data that's coming from Dutch Data Analytics. For somebody like me who has construction background, this was actually a little bit surprising. Of course, there's no owner that would not be concerned with the budget or the cost of their project, right? But in construction, we have many strategies through contracting by which we might be able to control budget. Quality, whatever is a specification of our project, is dictating that. And when it comes to safety, of course, we've hired our contractors and we rely on them to keep the job safe. And design, of course, this is another question that's being asked in the design phase. So every day that the project is being delayed, it's impacting the bottom line. We work with companies such as Facebook. Facebook today is building 12 data centers all at the same time. For those of you who may not be familiar with these projects are projects that are roughly around $300 to $500 million, and they get finished within 10 months. So for an owner like Facebook, you're roughly looking at $50 to $60 million that is being spent every day to make sure that projects are being kept on the schedule so they can actually open up the new data center and make sure you will be able to upload your images and data that you would like to share with your friends and family to their platform. So schedule becomes extremely important. For us to better understand why this is really happening to the bottom line of our project, I want to take you back to what we do in construction in terms of project controls. For many years, we've been promoting how we can support projects by enabling systematic planning practices, performing monitoring, and adjusting performance. Over the past decade, we've seen a surge of projects where now the lean construction concepts are being adopted and adapted. We take projects through pool planning processes, we make the work ready, and we try to educate them through who does what work in which location in daily huddles, and see what we can learn from that performance and improve the basis of the schedule. So in the context of planning, monitoring, and control, there are 4 specific problems that are impacting our performance on planning and execution of projects. Number 1 is, as an industry and as an academic community, we've significantly improved the basis of how projects can be planned. The concepts of planning and the scheduling have been around for quite some time. And over the past, as I said, 10 to almost roughly 15 years, we've seen a lot of these concepts from lean community that are actually being practiced today in construction projects. But anecdotal observation from a large number of projects that these days we are engaging is actually showing that there's this huge room for improvement. Many of these projects where we are bringing these best practices rely on champions that can make sure that people are being able to follow the new culture of adopting lean practices. And many leading researchers in our community, including Raphael Sachs and others, have been publishing a number of publications that shows that in the absence of having these champions on the project, there's always an opportunity that the project team may revert back to old control practices. So we will not be able to support that. The second problem is, while we create plans, many of our construction projects and teams are unable to execute a plan. So in my lab at the University of Illinois, over the past 14 years, we've been capturing data on the root causes for delay that are impacting plan performance. And there are many reasons. Plans keep changing on job sites. Teams would walk into a room, the work area is not available to them. productivity is being underestimated. We have inclement weather days that's impacting. Our analysis shows that 79% of these root causes for delay are preventable. All we need to do is to make sure that the project team is understanding where the problems are, and they have an opportunity to, address those problems proactively. The third problem has to do with communication and how we measure performance. Many of our job sites, ironically in 2020, we still rely on 11 by 17 sheets for people to walk around the job site in color code drawings in terms of how much work has been done in various locations. Of course, we've looked into digitalization, and now people use iPad and Android devices to electronically capture this. But basically what happens is we rely on people to walk around the job site, do the documentation, and oftentimes we don't have an opportunity to communicate that before we all get together in a coordination meeting. So essentially from the time that the problem happens to the time that the owner, contractor, and the subs really understand where the problems are, we've effectively lost 1 week of work. Now, map this out in the context of the data center projects that I mentioned, you can actually see there's a huge room for improvement with respect to communication and performance measurement. And the last problem has to do with, unreported progress. Still in 2020, many construction projects rely on regional directors for scheduling that come with these schedules, and they rely on these individuals to go back to projects and help them improve the basis of their schedule. What is really missing is that feedback loop to make sure that these individuals understand what happens on the job site, bring that data back into the schedule so they have actionable insight that can be used to as a basis of improvement. So in the context of these 4 problems that I mentioned, I was really fascinated to see how we can address them by tapping into emerging and existing data. So I really didn't want to change what we do today with the type of data that we have on the job site. So from one end, I was really fascinated by BIM, given the background that I had roughly around 15 years ago when I was practicing BIM with some of our colleagues at the University of British Columbia, measuring ROI for MEP coordination. But I was really interested to see how we can tie that into schedule, not just as a 4D beam, but rather at a 4D beam that matters to superintendents at a production level. So we can set a visual representation of what is expected to be done on our job site every day. We know who does what work in which location, and what is the sequence that needs to be monitored proactively on the job site. On the other side, we've also seen a surge in how visual data is being captured on the job site. These days, we call them reality capture, and there are many form factors. We see people who are walking on job sites, taking pictures using their cell phone devices, which is what you see on the top left corner. We have professional photography companies that are being hired to take photos for us. We have partners that bring fixed cameras on job sites, and they provide time-lapse photography. Using action cameras or 360 cameras for indoor videotaping is extremely popular these days, especially with contractors in the US. We've seen a surge of drones over the past 5 years that, it's basically commodity. You fly them and you have opportunity of capturing this visual data. And of course, for more than a decade, as a community, we've been leveraging laser scanning capability, but perhaps at a lower frequency compared to other types of data you see. So what I was really fascinated was to see how we can tap into BIM plus a schedule to represent what is it that is expected to be done, and tap into these images and videos that everyone on the job site understand to represent what is it that is exactly happening on our job site. So basically, I wanted to come up with this type of representation that we will be able to take BIM, connect that to the schedule, and overlay that on top of our photograph. So by looking at one picture, if you're the owner, if you're the contractor, or you're the sub, you can understand what are the areas that are on the schedule and what are the areas that are problematic, whether these are actual problems that have happened on the job site or potential problems that are about to happen. And maybe you have an opportunity to proactively address that issue before it happens on the job site. So in the context of that, my research team has been working on the theoretical foundation for project control system that I would like to call it data-driven. But not every type of data that is visual. And the way I've been always thinking about this is in form of this Venn diagram, that our BIM connected to a production level schedule can set the basis for reliable planning in the first place. Then as we capture photographs and videos on the job site, perhaps we can perform mapping of the reality in a three-dimensional environment against that BIM model, so we can use the visual data as a feedback to the BIM. Use the combination of the two to fill in the gaps that we have in maturity of the model, the design model, to improve the basis of coordination and communication from a progress perspective, from a constructability perspective, or safety. And then contrast the two using artificial intelligence algorithm that in the context of a schedule, I will be calling in predictive schedule analytics, so we can proactively manage risk that is about to happen. So now you would see the A of ABC on the top left corner, and digital twin, that will be that combination of BIM plus the reality data, the computer vision based models. So of course, we wanted to see if we can automatically generate these visuals that we have. See if there's a way that we can automatically align our BIM, or rather 4D BIM, against the photographs. Now, in earlier days, we were tapping into time-lapse photography, and it was rather straightforward. We can actually tap into some straightforward perspective endpoint algorithm methods that would bring BIM into alignment with one image. And because the camera is continuously taking images, your sequence of data would always be located in the right spot in the context of the image. But then immediately we realized we're always limited to whatever you see from the field of view of the camera. What is going to happen indoors? We always want to capture images from areas that matter. What can we do with the wealth of images that are being captured around the site? These days, people are flying drones. They're taking images with cell phone, the 360 camera, and nobody wants to use multiple systems. Everyone is passionate about one integrated environment where you can actually map your entire visual data against that design. So the question in more academic form was, how are we going to be aligning these images against our 4D BIM automatically? Now, for those of you who may not know much about computer vision, what we do in computer vision is dominantly use a model, which we call a pinhole model, for representing images. And what that means is we map out intrinsic and extrinsic parameters for every camera that in mathematical form, it's an 11 degree of freedom problem that would map every individual pixel in the image against a position in space in 3D that will be represented with X, Y, Z. But then this would have required us to understand how every feature within the image match against BIM at different levels of granularity, which was not easy because, as we all know in civil engineering, modeling is a task of creating an abstraction of the reality of the site. So we mapped the problem slightly differently. We said, what if we come up with a new algorithms or a pipeline of algorithms that would automatically organize our images in a three-dimensional environment, generate a 3D representation of the site, find location and orientation of images against that. So now our problem from an optimization perspective has grown. Not only we have to solve for the cameras, but also we need to find that 3 degree of freedom representation for every point that is going to be mapped in this point cloud representation that we have on the site. Once we achieve that, then we will be able to have the reality of the job site on one side. Then we also have the BIM plus the schedule on the other side. And then we can work on algorithms that can bring the two into the same environment, where now you will be able to overlay your BIM against that reality. Now, this entire scene would be in a three-dimensional environment, but I also wanted to, do this for images, because if you talk to superintendents, foremen, field engineers, you would immediately realize that they're not very keen to leverage point cloud data directly. Rather, they like to interface with that data through images and use the point cloud as a basis of measurement. But because we are actually solving for these 11 degree of freedom problem for every image, now we have an opportunity to use that transformation and back project our BIM model into every image. So now essentially we can generate augmented images without using any dedicated hardware, where you can exactly see which pixel in the context of the image would match against which element, location, and work package in the context of your model. And all that mapped against the timeline slider. Once we achieve that, then we can start looking into comparing the two in the context of the schedule and see what are the techniques that we can come up with that can automatically color code models. Again, areas, work packages, locations, whatever granularity you want. Color coded in red for delays, areas that are on schedule in green. Not only we wanted to understand what has gone wrong or what has gone according to the plan in the past, we also wanted to forecast this into the future. So we wanted to see if we can come up with a body of new algorithms that can forecast risk for potential delay in the future. So when the project team goes into the coordination meeting, they can really rally around this location that's been color-coded in orange and say, what are the root causes for delays that are happening on this location? What are the constraints that we have? And how can we revise these schedules so we have a more reliable performance? Then, perform your weekly coordinations around this meeting. This system has been scaled today, and it's being used on hundreds of projects in the US and around the world. I'm just showing you one example, and I'll get into the details of that in a moment. But this is with Clayco Construction Company in the state of Missouri, United States, where you can actually see that behind the superintendent's head, the system is being mapped, and there are two locations color-coded in red and yellow. These locations are at risk of delay, and the team is really rallying around these locations. All the subs and trades that are engaged in these locations are discussing what are the root causes for the delay, what are the things that are not going to start on schedule, so we can proactively avoid these problems before they happen on site. So now that I've shown you what the end result of this system looks like, I want to take you back and walk you through one step at a time, starting with the most basic functionality, which is the ability of modeling the reality on the job set, or mapping it rather. And there are two specific questions from a scientific perspective. One, how are we going to transform these unordered site images into 3D models? This needs to work outdoors as much as it works indoors. And how are we going to be automatically aligning images against our 3-dimensional models? So I've already gave you a sneak preview of how it looks like, but again, we map this into a computer vision problem, a study that we call structure from motion, in terms of understanding what is the motion that we have between these frames, understand the overlap that we have, and see if we can map that out into a 3-dimensional environment. So we try to do that first. Then we wanted to work on algorithms that can bring BIM and reality into alignment, and then work on computer graphics algorithms that can simply back project the BIM model into the context of our images. So now mapping this out in the context of a computer vision problem, that means our input would be images, and perhaps in these images we can perform what we call a feature detection procedure that can find certain pixels with certain mathematical characteristics that are distinct enough that we might be able to find them in other images. And the output that we're expecting is the structure, which is the 3D location of every one of these points that we've observed, and also understanding the motion, rotation, translation, and possibly intrinsic parameters of these cameras. So we can actually map this out in terms of an optimization function where we will try to initialize the problem by triangulating the points in the 3-dimensional environment and then back projecting them in a 3D form. So let me stay at a really high level and walk you through the procedure. So more than a decade ago, we started working on these algorithms that treat every one of these images that we have on the job site, regardless of how much overlap they have, to see if we can find these distinct features. Then we wanted to see if we can find mechanism by which we can match them in a pairwise fashion, see if we can find consistent motion across them through some model fitting algorithm that we call RANSAC. And fundamentally, we will be looking to fitting a epipolar geometry that in computer vision terms we call it fundamental metrics, that would guarantee that we are not being challenged by redundancy that we typically see in the design of our infrastructure systems. Once we have these tracks formed based on our features, we will be able to triangulate them using direct linear transforms, back project them into every one of our images, and solve for this optimization problem that I'm showing you on the screen using a Levenberg-Marquardt algorithm. What this procedure does is that it gives us an initial representation of the points in 3D, and it finds the right orientation and viewpoint of every image in our 3-dimensional environment. Then we will be able to use this in a pipeline of dense reconstruction plus model fitting capability. And what that means is that we will look into photometric consistency across our images. And this type of method would require structure from motion output, what I described before, as an input to the process. So we can actually triangulate these positions in a 3-dimensional environment, so we can actually generate the basis of a dense representation of the scene. Now, obviously, because of the limitation that we may face in terms of visibility, we want to be fitting surfaces into certain holes, and there are body of algorithms for surface reconstruction. For example, you can fit what we call Poisson surfaces into the generated models. So, once you apply this set of pipeline of algorithms, a structure from motion followed by some form of multi-view geometry, by some form of a mesh modeling algorithm, you can actually provide deliverables for construction projects. And these deliverables will be the following. Regardless of how images are captured, whether they're with a drone, they are taken with a 360 camera, or maybe with a camera that is fixed on a tower crane, we will be able to map the job site in a two-dimensional form, 2.5D, which is an orthophoto that has the depth information, at the same time map that in a reality scene. So I want to show you one example from the project that I was showing you earlier. If you recall the project that I showed you where the team was gathering on the largest screen, it was actually a $150 million project in St. Louis. So you can actually see a high-rise structure on the right side, concrete structure with a parking garage on the left side with that big excavation hole you see on the corner. In this case, all kinds of images were being uploaded into the system. Images taken with a drone, images taken with a cell phone, and the combination of them is being mapped into a three-dimensional scene. And it gives you this image-based experience where you can click on every one of these individual images. You can dive into a high-resolution image. And on that image, because you have the point cloud as the backbone of your system, you can perform measurement. You can measure length, you can measure areas, volumes, and use that as the basis of your communication. Of course, we wanted to do this over time, so maybe the team would be interested in performing the capture once a week. Maybe it's a fast-paced project, so they want to do the capture every day. So we wanted to create a scalable architecture that would let this type of system work over time. So we worked on a number of algorithms that would tap into this type of consistency that we see in features, because not everything changes every day. And we created a KD3 structure around these feature descriptors that, it's roughly around 128-dimensional vector space. And we would adopt a number of search algorithms. In this case, for example, we use a fast approximate nearest neighborhood search. And we would use that in the context of an optimization process. So every time a new set of data is being captured, we can actually use the model from the previous capture. What we would do is we would match the features from the new capture against that. And when we are running for the optimization, we would add that constraints of the match to make sure that we can actually optimize registration of this point cloud against the previous one. So now we can actually generate four-dimensional models. Now, fast forward some 7-8 years that we've been working on these algorithms, these systems are being used at the commercial grade. So this is an active project in city of Chicago in the United States, where Oracle, the company that offers Primavera solution, I'm sure many of you are familiar with, is actually using this platform at a commercial grade for their own project. So in this case, you can actually see there are many orange dots on that timeline slider that each and every one of them shows you one day of the capture on the job site. You can actually dive into any of these images, and on that image, you can actually leverage the 3D scene and the 2D navigation map simultaneously to perform your measurement, documentation, and management of the scene. So what does it look like in 2D? So let me take you to the 2D interface. That means you can actually overlay your deliverable from the computer vision process over your Google Maps, especially if you have GPS data or use ground control points. And if you have 2D drawings, you'll be able to also overlay that on top. So now you can actually see reality against the plan, not only in 3D, but also in the context of the 2D environment that I'm showing you. So now that I've shown you some of these capabilities, I'm going to speak about how we're going to enable the alignment of images against BIM. Most of what I've mentioned to you so far is the ability to map the scene in a three-dimensional scene. So for solving the alignment, initially we wanted to automate this, but we've gone back and forth on this, and I'll get into the details of it. Why? Basically, what we will be asking every project team to do is to introduce a number of control points. At minimum, we need a total of 3 control points that can solve for this 7 degree of freedom similarity transformation between our BIM against up to scale point cloud. Once we have that, BIM can be matched against the reality, and because the reality models are being mapped over time, then you'll be able to automatically achieve BIM against image alignment, regardless of the date. So now you can explore a time machine that you can go into every location you desire. You can focus on that image, change the date, find the most relevant images over time, and see your BIM model that's being automatically overlaid on images. Now, scaling this up in terms of every project, no matter what type of data they have, no matter how much capture they perform, and at what frequency, we had to work on a number of optimizations. And I'm not going to get into the details, but there are a number of algorithmic optimizations that we've introduced to the process by changing many steps that are happening in this pipeline of algorithms. And this is one of our works that was published in Transactions on Mobile Computing in IEEE. That can actually show how more modern frameworks for structure from motion can enable faster performance. So in this case, we're able to come up with methods that are 10 to 12 times faster than the state of the art, while our methods is actually going to show consistent or rather smaller differences. So we actually were able to benchmark orientation and viewpoint of every image in our validation process against the ground truth. So once we had this optimization done, and we had a system that was really working, we implemented it at a scale across the board. We use this in the US, in California. We use it in Illinois. We used it in Japan with Taisei Corporation and many other organizations that you see. Roughly even, we reached a total of about 126 captures in early days. We realized that, well, we really need to figure out a number of things to support this process. One, we want to make sure that we have techniques that can easily render these point clouds, regardless of their size. So, I had the opportunity of working with Jacob Lin, who's now an assistant professor at National Taiwan University, to come up with a level of detailed systems on how point clouds can be rendered in an octree form so we can visualize them in a web-based system. So you see some of those examples here. But then we also realized that, following our standard structure for motion does create a few challenges. One, there's never a guarantee on completeness of the scene. Oftentimes we provide guidelines on how capture should be done, but there's no guarantee. You would end up having locations that are, exposed as whole. And what that means is that maybe the team has to go back and do more capture. The second problem was, because we are running this optimization, we may run into these issues that we are really not optimizing for the global problem that we're solving. So we're getting stuck in that local optimum problem. And what that means is that there's going to be drift, or there's going to be these loops that are not going to be properly closed. And for those of you who've been working with computer vision algorithms, when you're actually working on reconstruction from images, we always have this issue with our transformations that are seen without using any control points or GPS data will be up to scale. That means it's unitless, so we are not going to be able to measure that. So instead of following conventional computer vision algorithms, we thought, what if we try to bring something from our computing and civil engineering back into the computer vision domain? What is that information? BIM. Of course, our project teams are always using BIM as the basis of design. What if we try to leverage the geometry and semantic data we have in BIM to improve how we actually generate point clouds from images and videos? So instead of using BIM after the 3D reconstruction, what if we find a way that we can find the most informative images on the job site automatically? So maybe we can call them anchor images, and then bring our models into alignment against these photographs. So we would pick a few anchor cameras, and we'll solve for these perspective endpoint algorithm problem, where the BIM model would be overlaid on some images with the help of a manual input. Now, once we have the anchor camera, then we can figure out how every other image that we've had on the job set can be brought into alignment. So basically, that anchor camera would be introduced as a constraint in our problem. So now, instead of following a standard bundle adjustment procedure in our structure for motion, we can map this into a model constraint structure for motion, or in our terms, we can call it BIM constraint structure for motion. And what that does is that it would optimize our process. So let me visually show you what it means. That means we would start with an image that the user is guiding us on how BIM should be brought into alignment. Then we would go into our optimization process, and this is completely automated. The rest of the images, one at a time, or a group of them at a time, will be aligned. And if the system fails in bringing some of the images into alignment, we can bring them back to the user so the user can help us with more distinct views that do not have enough overlap. So this procedure was able to reverse the problem for us. We would use BIM as a starting point. And of course, we had to benchmark to see what is the contribution that we can bring back into computer vision and computer graphics. Now, In more modern terms, Microsoft at the commercial grade came up with a solution called Photosynth that was based on a structure for motion algorithm done at the University of Washington. And this is the state of the art. So we had to benchmark our performance against standard data sets that are called Middlebury, and also introduce our own construction data sets. And we're able to perform that. And as you can see on the data, using validation metrics to measure the error on rotation and translation, we can actually see we can lower the errors that are typically happening. So what does that mean? That means we can minimize those drifts that we used to see. So when it comes to aligning our point clouds against BIM, we can actually have more modern methods that can actually improve the basis of these registration. That was our first finding, that BIM basically as a constraint can lower these drifts and keep the angles upright for us. The second one is introducing BIM as a constraint can actually help us register more images. So I'm showing you an example, one image from a data set, and we ran this using our standard structure for motion procedure at the same time as a complete reconstruction. So as you can see, we were able to improve the basis of that. Now, in earlier, commercial grade application of this solution, we were dominantly focused on outdoors. And we were hoping that people would come back and say, we can always go back to our laser scanning practices for, indoor mapping. Or we thought, at some point, maybe we'd be able to bring drones, thinking a little bit immaturely that, these magnetometers that are placed on the drone are not going to be impacting navigation capability. But while we were working on these algorithms, 360 cameras came out. And these cameras are extremely popular with construction teams because they're low cost, they're simple to use, they're quick to capture, and they're really scalable. You can put them on a pocket, you can mount them on your hard hat, and you can walk around and do these type of captures. So we've actually looked into how we can optimize these algorithms. So now for not only indoors, but also outdoors, you can place your camera over your hard hat, walk around the job site, do a complete video capture. Now, these videos can be imported into the system. So now we can actually create more of a Google Street View experience where we will place these donuts that are subset of the frames extracted from the video, and we would automatically generate a color floor plan, that ortho photo that I mentioned to you before. Of course, there's a point cloud that's being generated, but the users don't necessarily need to see that. So they would be interfacing that from an image perspective. Then we tapped into bringing models, and intentionally we decided to adopt an API that would bring many different file formats of models as opposed to constraining ourselves on some of the more academic type of representations that we use. This is how it looks in terms of the 2D representation. So every location on the job site, for example, level 15, 16, 17 on the building project, you would have a color floor plan, and you can automatically see locations that are being mapped against that floor plan. When project teams bring their 2D drawing, we can also map that against that environment. So now we can create this entire street view experience from the same type of capture, but this time indoors. As you can see in this case, I'm showing you a project. This is captured with a 360 video. The video is being transformed into a reality model. Images are the interface. As I'm walking between these donuts, you can actually see there's a little point cloud that is being rendered on the scene, but everything is entirely in 3D because of that point cloud. And what that means is that on any of these images, I can perform my measurement. I can select any of these points and use inference from images. So every pixel from the image becomes measurable beyond completeness of my point cloud. The navigation map is going to help me navigate myself on the job site. As you can see with COVID-19, this is extremely popular these days. People are actually using this for remote monitoring of progress and quality. You can orient yourself against a 2D floor plan, so you can jump between different views as it relates to that floor plan, and interact with the system entirely from that perspective. You can also see this from a point cloud perspective. So let me play that a little bit here for you. What I'm going to do is I'm going to go ahead and put us in a first-person mode so we can walk around the job site, so you can kind of get a feel for completeness and the density of these models that are being generated. Now, everything I showed you was in 3D. Now, this is the 2D representation of that, and that means your reality data in 2D can also be mapped against the design data in 2D. So if you have individuals on the job site that are more oriented in 2D, you don't have to restrict yourself or require them to use a model that may not be IFC issued for construction necessarily. So now we're going back into the 3D-dimensional environment and we are activating BIM. So now your point cloud and BIM are integrated within a web-based environment. You can go into any of these images that you desire, and by playing with the opacity and transparency that you have in the scene, you can actually use BIM as an overlay. You can select any components and tap into the metadata that we have in our BIM model and contrast it against the reality. So you can see what is there on the site, your picture, versus what should be there. And depending on how accurately you've brought these two models into alignment, then of course you have something that you can use as a basis of your measurement. So you can annotate it and document any quality issues. So now this system, as I mentioned, is also being used at scale on many of our job sites. I've shown you how we can bring BIM into alignment with the reality model. I'm going to speak a little bit about how to automatically track progress. So once we have that data, regardless of your interface between 2D and 3D, the question was, can we automatically recognize how much work is being done? So a long time ago, roughly about 10 years ago, we worked on in a paper that was published in International Conference for Computer Vision on how we can reason about visibility and occupancy of the scene and map this into a machine learning problem where from BIM and where images are, we can kind of get a sense for where physical presence exists on the job site or is expected to exist and contrast it against the reality. I'm not going to get into the details, but in early days, we mapped this into precision recall and we realized that we can get somewhere between 80 to 90% detection accuracy. And from an academic perspective, this was really great result, something that was publishable. But in terms of being able to use that for the practice, it had a lot of room for improvement. Let me show you some failures. If you use physical evidence to track progress, you would end up having these types of false positives, where if you see on the example that I'm showing in the top left corner, form work is wrongly being detected as progress has been made on the job site. So the element is being color-coded in green. Or if you notice at bottom lower example, I have a false negative example. That element was expected to be detected, but we didn't have enough visibility, so the system is not able to handle occlusion properly. So first question we ask is there a way we can improve our ability to recognize progress by tapping into appearance data? Now, this is not entirely a computer vision problem. There's a lot of issues with our computing in civil engineering domain that still can be addressed. One challenge was, if you have to recognize progress, let's pick concrete structures as an example. You should be able to recognize concrete against reinforcement bars, against formwork, against waterproofing, against insulation. And what that means is that in your schedules, you should have enough details to be able to recognize these different granularities of the work. Your model, your BIM model, regardless of what discipline you're looking at in the model, should have the right maturity in terms of the LOD to represent these details. And lastly, we need to have a formal way of representing these sequences. What is it that we are expected to see for concrete, drywall, and so on and so forth. So we actually mapped this into a multi-view inference problem. And what I mean by that is we wanted to see if we can back project the BIM model into every image and think of Photoshop. We wanted to see if we can Photoshop parts of the image that would correspond to our BIM models and elements and tap into the material that we are expecting to see in each and every one of them and take samples off of them. If we have many of these samples, then we can map this into a multi-view inference machine learning problem and see if we can recognize what is it that we see in the pictures and beyond our physical recognition, recognize what kind of materials exist on the job site. So we formulated the problem in the following. We want to solve for this material recognition problem, and we've done quite a few work on this. This is the latest work that we did in this area. That this is published on Conference on Computer Vision and Pattern Recognition conference in 2016. And the idea was to see if we can tap into geometry and appearance data at the same time. So we mapped this into a deep learning problem, but instead of treating deep learning as a black box, we wanted to take the output of the last layer, concatenate that with other features that we capture from dense scale invariant feature transforms that would map texture plus color being mapped in hue saturation value form, concatenate them, and pass them into a supervised discriminative classifier that we can see if combination of geometry and appearance can improve how we recognize progress and recognize materials. So this has actually been benchmarked against the state-of-the-art for texture and material recognition and computer vision. And for those of you who are interested, you'll be able to tap into that. As you can imagine, we had to introduce a new library of materials and code that if others would be interested in building upon this work, they will be able to tap into our code and use the data for future research. We brought this back into the same problem of construction monitoring, so we were able to use that to see if we can improve the basis of recognition. So this solves the first problem that I mentioned to you, which is now maybe beyond geometry, we can also look into appearance and see if we can improve the basis of our recognition. The other problem that we wanted to solve was, how are we going to be dealing with these occlusions? And what I mean by that is, if there's a foundation and there's a column that we see, is there a way that we can leverage the interdependency we have between the elements to say maybe that element that is severely occluded or completely occluded can be recognized as work complete? So we went back to the literature and we came across a work, a classic work that was done by William Ibbs and late Diego Echeverri at the University of Illinois back in 1991, that they were fascinated by automation of construction planning. And they were looking into how constraints for sequencing can be formalized. We thought, what if we tap into these relationships and see if we can learn them by tapping into the model? So we looked into how we can tap into IFC schema, tapping into the type of inter and interclass relationship that we see between the components, bring these formal sequences out, and use that to improve recognition. I'm not going to get into the details of it, but this is a publication in the Journal of Advanced Engineering Informatics that we were able to also improve the basis of recognition by another 6%. I showed you how we can automatically track progress, but I've not mentioned to you how we can identify risk for delays. And what I mean by that is there a way we can map these rates of production that are being captured on the job site, so we can go back and color code locations based on risk for potential delay? So this is rather new work that we've been performing for about 4 or 5 years. Now we're about to be publishing this work after this has been commercially offered through a number of platforms that we've released to the public. We've introduced a number of metrics that basically, in very simple terms, track rates of production on the job site and maps this in the context of work packages and the trades that we have. So for tasks that are about to start, we measure their readiness, and for tasks that are ongoing, we measure their readiness to be completed on time. Then we use a new formulation to map risk at the location level by assuming that tasks are mutually exclusive, but are dependent on one another in terms of locations, and be able to highlight risk at the location level. So what does it mean in the practice? That means if we can actually scientifically solve for this problem and bring it to the practice, now our project teams can go into a coordination meeting, and instead of going around the room discussing what has gone wrong or right over the past week, one company at a time, we can rally the team around one location at a time. This is a project team in Chicago, and you can see on the screen there are 5 locations that are sorted based on severity of risk for potential delay. And the team is discussing what are the root causes for the delay. And you can see the superintendent for concrete is actually standing up and is engaged in the conversation on how we are going to tap into changing our schedule so we can proactively address the source of the delay that we see on the job site. So we actually benchmark performance improvement using construction metrics beyond our computer vision metrics or AI techniques that we typically use for validation. And we're able to show to this project team that in the span of 6 weeks, after doing a control phase, introducing the platform to them, and then measuring performance, we were able to take them from percent plan complete of 46% to 70%. With the platform, all they did is really brought transparency. You can actually see where the problems are. And if you take an action, of course, you can improve the basis of the performance. Now, this system is also being used end-to-end in other projects. So I'm going to present you a second case study. And this case study is also available for download. That on a project in the state of Georgia, we're able to map performance over an entire duration of 12 months. And the team leveraged the system, and they were able to finish the project 4 weeks ahead of the schedule, which is significant improvement compared to those numbers that we're showing you in terms of average performance in the industry. But they also wanted to see what is the impact on every persona you have on the job site. Does it help the superintendent improve the basis of updating progress? Does it help minimize some of our scope change orders? Because now it shows you what is there versus what should be there. And does it help us with remote monitoring? Now, this is before COVID. With COVID, this type of solution is extremely popular to not go to the job site and remotely monitor progress and quality. So again, we're able to demonstrate that there's room for improving the basis of remote monitoring by 50% for a number of stakeholders that are engaged in this project. Everything I've showed you is what has already been commercialized, and now it's being used after the research that we've done over the past decade. What I'm going to be speaking to you right now is some of the things that are coming out from the work that I've had the opportunity of being engaged in. And one question was, is there a way we can improve the data capture? You know, as simple as placing a 360 camera is on the job, on a hard hat. There are many job sites that people just don't want to walk around the job site to do the capture. So they come to us and they say, is there a way you can help the drone to autonomously navigate? Of course, there are regulation issues, but you know, from a scientific perspective, there are a number of problems that we haven't solved yet. And these questions are, you know, is there a way we can guarantee resolution of the point cloud? Is there a way we can either solve those completeness or critical views? So let me show you some visuals. Those incomplete coverages that we see from time to time, is there a way maybe with a systematic plan we can address inaccuracies in our reconstruction or low visibility, because we wanted to make sure our point clouds would have the right resolution, maybe, you know, 1 centimeter, half a centimeter per pixel. And the question was, can we leverage our BIM and previous point cloud as a strong prior to improve the basis of planning for the future? So one of my students, Amir, and I have been working on a number of algorithms to see if we can improve the basis of visual data capture independent of what kind of robotic platform is being used, whether it's a drone, whether it's a ground robot. Use simple terms so people can actually create the plan for the capture with rough terms, and use metrics such as sampling distance, visibility that we want to have, redundancy in visibility that can support our multi-view inference, and viewing direction, while also making the system in compliance for line of sight requirements to keep line of sight to the drone and battery requirements. So now it's a multi-objective optimization problem. And what it means is that if you map this out in the context of a BIM model, you can go ahead and see your model color-coded based on whether your new mission for the capture on the drone or ground robot can achieve the metrics that you desire to have on the job site. So I can actually show you an example of this prototype. This prototype has been used in the US and Japan by Taisei Corporation. I'll show you an example here in the US, where the user initially creates a flight plan in 2D, but then you'll be able to see the flight plan in a 3-dimensional environment against previous point clouds and the BIM model. So you can explore that, you can adjust it, and then you would run an optimization that provides you with a new input on how you would be able to revise your flight plan and feed that automatically for today only with DJI drones that can achieve the type of resolution and some of those other constraints that I mentioned to you. Now, of course, you will not be surprised if you approach and ask if you can do this on ground robot. Now, I don't do any hardware myself, and I'm not interested in that component of the work at this stage. What we've been only working on is operating systems that can be mounted on any robot that can provide visual surveying capability and visual capture. So, we acquired this ground robot, and we mounted it with 2 very cheap laser scanners that are at the back of the ground robot. Each of them costs only around $150, literally $150. And there's a 360 camera that's sitting in front of it. A user with a joystick would manually operate this on the job site. It would learn a map, and then you would run it through that algorithm that I showed you before, so we can create what is the most optimal plan for operation, and use that as a basis of repeating the work. This is actually ready for demo. If you ever visit us in Chicago at Oracle Innovation Lab, many construction companies that are visiting that lab, this system is being demonstrated by Oracle as one of our partners. Now, you will not be surprised if we've also been approached to see if this can be mounted on other robots. We've had the opportunity of being a partner to Boston Dynamics and Faro. Both of them have been great partners. And we are exploring to see if this modality of the capture can support all of those analysis that I showed you before. I love this platform, but it comes at a cost. The ground robot costs roughly around 72 grand, and then you obviously have to add the element of the laser scanner on top of it. The other problem that we've learned is it's great to show where the risk is, but can you tell us how we can introduce changes? So we tapped into more analytics on the schedule. One of my students, Fuad Amr, and I have been working on bringing back some of our old techniques in the scheduling, but map this out in terms of natural language processing and machine learning. Can we tap into our historical record of projects and see if we can learn best practices and offer a recommendation? So no longer just color coding orange for risk, but once you see the risk, we can give you the top 5 recommendations on how issues can be potentially addressed in the future. So everything I've shown you so far has been things that has to do with progress monitoring, bringing that as a feedback to the plan, and the basis for control algorithms. There's more work that we've done on detecting and tracking workers, equipment, recognizing their activities that I don't intend to get into in this presentation. So I want to leave you with a few takeaways. On the technical side, as much as we've been working on applying some of these AI techniques in construction, there's always a room for bringing some of our own contributions in computing in civil engineering back to the AI domain. One, I showed you on the 3D reconstruction side that our knowledge of geometry, our knowledge of civil engineering, and what we do in computing can actually improve the basis of many algorithms for reconstructing scenes. I showed you a number of techniques that combination of geometry, appearance, and reasoning using a structured data can improve the basis of recognition. And when it comes to inference, I've showed you how potentially natural language processing can be applied. So instead of relying on many techniques that goes back into 60s that are earlier systems of AI for planning were being introduced can be improved so we can automatically provide revisions to the schedule. The practical significance of this is pretty simple. All we do is we just tap into existing data that project teams already have, images against models, to see how we can improve the basis of planning, how we can coordinate and communicate the schedule. And it's really all about transparency. If the project teams can really see where the problems are, perhaps they can proactively address these problems before they happen. I showed the examples of improving the predictability of a schedule. I didn't get into quality much. And of course, if you have any owners on the call today, or if you interface with owners, I'm sure you appreciate how this can potentially support payment applications and billing process. So this is really a solution that brings win-win for every party. It puts the owner, contractor, subs, and designers on the same page on where the problems are. So now that I've spoken about the technical problems and practical problems, I just want to take a moment and speak a little bit about the path forward. I think this is a really exciting times for all of us in computing and civil engineering, and we're just starting a great conference on that. In the US, AI is at the national spotlight. President Trump put a task force last year to explore how investment can be made more on the AI so we can tap into more enterprise-grade applications. But as you can imagine, when you talk to folks that are pure AI, they tend to focus on problems that are constraints by huge quantities of annotated data. That simply doesn't exist in construction. We all think that it exists. Of course it does, but it's not directly and readily available to us in academic community for all kinds of reasons that I'd be happy to speak to. I've had the opportunity of teaming up with a team of 9 other researchers at the University of Illinois and Carnegie Mellon to see how we can actually bring this AI back into AI in construction, back to the AI community. The AI community is really excited about this opportunity based on some of the works that I've shown you, because different from conventional AI, AI folks would have to be constraints with the application logic. So when you look into the learning loss, for those of you who are actually working on machine learning problems, you can actually see the application logic would actually be controlling this formulation of the loss. And there are many data problems that are not easily exposed, but when you bring it back into the core basic AI, there's a huge room for improvement. For those people who are at the core AI, they see this as another opportunity. Construction has open environment. There are multiple modalities of data that's being captured, and there are very clear use-inspired objectives that we can tap into. So solutions in construction can be tapped into, can be guided by taxonomies that you're going to be hearing, in the next, day or two on what is the state of the art on that front, and many metrics that can actually verify success beyond simple precision and recall, metrics that matters to those of us who are working in computing and civil engineering. But how can we interface this? I think it's a mission that is in front of all of us to tapping into. And the question is there a way we can bridge this gap between what we do in research, which is coming up with prototypes and validating the concept, to solutions that the industry can use? And I really think that our community is at the right opportunity in time to get to this center of research with education in experiential AI, and also entrepreneurship, taking ideas from the lab, working directly with the investment community, working with technology companies or startups to tap into their data. So instead of directly interfacing with the companies that are less willing to share their data, you would specifically focus on problems that matter to that technology company that can manifest itself in terms of the application to the practitioners. So our consortium, beyond our 10 individuals, also includes 45 architectural, engineering, construction, and owner companies. We have had the pleasure of having Oracle, Autodesk, and a few other parties in this consortium. And I would like to open up this to our entire community. If you're interested in being engaged in this opportunity, please do contact me. I'll be more than happy to speak to you about what is this consortium that we formed on AI for construction, and how are we going to be interfacing between what we do in academia, what happens in the startup community with AI and deep learning, and how it can manifest itself in terms of the application. So that's all I had to share with you. With that, I just want to quickly acknowledge the support from National Science Foundation and many organizations that have supported this research financially, from Intel to NVIDIA, from Caterpillar, and many other agencies. Many construction companies all around the world who've helped us with many examples of data that led us to the research and at the commercial grade. And of course, the entire team that is behind it. There's a team of talented people. Many of them are now professors and leading individuals in the industry that have contributed to this work. So I want to acknowledge their work, and I'm ready for any questions you may have. Thank you. I'm going to put my contact information back on the screen.
Thank you, Moni. Really impressive work. Congratulations. We have some questions from the audience. Let's start with. Actually, I would like to make a question by myself. Were you able to measure somehow the savings the system yielded to your clients? I know this is very difficult to measure, but could you somehow?
Yes, that's an excellent question, Eduardo. We only did this at a commercial grade. I did not do that through academic work. And we do have one case study that we published with a company out of Seattle. We've had the pleasure of working with them. They're an owner representative for one of the largest technology companies. And the project was roughly $1 billion project in the state of California, in Northern California. And on that project, we worked with them on measuring the impact of this to verifying payment application. So that was the only thing that we measured on the cost side that I can share with you today. That case study is publicly available for download, and you can actually see the number of, in terms of the saving for the owner rep in terms of their construction cost. And that's available through reconstructinc.com platform.
Okay, we read that. Okay, let's start with an easy one from Kayami.
Absolutely.
Yep. Can you read it?
Yes, thank you. Appreciate the question. So the question is, how can you generate point clouds for indoors? That's an excellent question. And, I want to go back to one of these slides that I was showing you on what we recommend today for indoors. And it's really fascinating. I won't forget, when I started working on outdoors and generating point clouds, I met a great project executive out of Tennessee. And he told me, most of the time our superintendents can walk outside of the trailer and can see what's really happening out in the field. Can you give us a system we can see what's really happening indoors? Because that's where it matters the most. We want to be coordinating our trades indoors. So I showed you the spectrum of capture mechanisms that are possible. The most dominant type of capture for indoors is using 360 cameras. The reason that we also like 360 cameras is, you can actually not be limited to a field of view that you get with a perspective camera. Oftentimes when you're working indoors, you're confined with limited corridors and viewpoint that you have. So a 360 camera can maximize visibility and capture features. And if you use videos, you can also tap into temporal continuity in the data. So you can actually look into some of these simultaneous localization and mapping algorithms beyond the structure for motion. So we've actually brought these concepts into equirectangular images that are being captured by these cameras. And now I can tell you this is the most popular form of mapping reality using 360 cameras because it's simple. And all you need to do is you turn the 360 camera on, you put it on your hard hat, you walk indoors and outdoors, and you can enable capture.
Okay, good. We have, let me remove this. We have a question by Jakob.
Thank you, Professor Beets, for asking that question. It's a pleasure seeing you again. So the question is the size of the training data, and if it can make an impact on object recognition, especially about recognizing building components and materials. Absolutely, yes. And there's a lot of buzz in this space at the commercial grade, which is, for those of us who have that academic background, is to some degree concerning because we know this problem doesn't easily scale for automated detection because we don't have the right type of data. So I want to go back to that slide that I was listing the 3 specific problems. One, if you want to enable this, this is not just the size of the data. Our schedules needs to be at the right granularity. Second, we really need to make sure that we can bring models at the right level of maturity at every discipline. So your M, E, P, and FP would rather be at 400 LOD so we can actually recognize them. And lastly, formalize sequence of construction. And of course, the size of the data matters a lot. Are we going to be able to capture that data as an academic exercise? I can tell you before my engagement with these technology companies, no. I spent many years, army of students, and also tapping into Amazon Mechanical Turk to see if we can crowdsource labeling of the data. And this was extremely challenging. At most, we came up with tens of thousands of images that were annotated. But if you actually work with these technology companies, there's an opportunity to tap into that data. So through this company that I've been engaged with, we've captured more than around 4 million photographs, 4 million. And you talk to other companies that are in this space, SmartBid, Josh Cannon, one of our good friends, they've captured over 6 million photographs that are actually being labeled. In their case, the labels are actually happening on safety. In our case, labels are dominantly on quality issues and progress that's being detected. So now for the first time, we have an opportunity to back project BIM directly into images and automatically create annotated data at a size that matters for these deep learning algorithms. The second opportunity is really synthetic data. We've also looked into how we can look into environments such as Unity, Blender, so we can photorealistically render models using library of pictures that we have in model authoring environments such as Revit. That also provides another opportunity. But data matters, data is king, and with deep learning algorithms being treated as black boxes, I would not be surprised to see some of these areas. If you want to explore them at the right academic level, we will be getting a lot of competition at the commercial grade. Second question that you've asked, an excellent question. The question is, can we come up with open training data? Absolutely. I think it is possible. It is going to take a significant amount of effort. We've been exploring that in the context of ASCE, DSA, Data Science, Sensing and Analytics community with Professor Nora Aguirre, my colleague, and a few others. We are trying to figure out how we can unlock that opportunity. But, commercially speaking about it, this is extremely challenging. If you talk to construction companies, they think that their IP is their data. If you talk to technology companies, that's the same. Oracle is a great partner for us, but it is going to be extremely difficult for us to tap into millions of schedules that have accumulated over the years. So, our approach to this is really establishing this consortium that I mentioned toward the end of my presentation. I have had the opportunity of working on this for the past 12 months, and we will be launching this initiative later this month. That for the next 2 years, we'll be specifically focusing on what are the problems that we can solve from an academic perspective, how IP can be formulated so data can be easily shared without violating anybody's IP, and how we can streamline this work between academic research, startup research and development into solutions that the industry can use.
Can you understand this next one?
So the question, thank you for the question. I think the question is, how can BIM and visual computing collaborate for the evaluation of a stop work, which should be extracted the amount needed for new budget for completion? I think the question has two parts to it. Thank you for the question, Rodolphe. Part of the question has to do with comparison of the two, and part of it has to do with mapping this in the context of earned value analysis. We've actually looked into the both. I have to tell you, on the earned value side of it, again, putting our academic hat aside for a moment, practically it's extremely challenging. Earned value is used a lot in process sector, in oil and gas. But when you talk to commercial sector, you don't see a whole lot of cost-loaded schedules in the first place. Even if you do that, you don't see work packages properly defined in the context of the model. If you get that type of data, yes, if you can recognize components, and if you use, let's say, CSI uniformat to automatically take off quantities and establish units of measure, then you can bring it back into earned value framework and forecast cost at completion. It is possible. We've done that manually. Automating that is more of a practical challenge than a research challenge. But an excellent question. Thanks for asking. All right. Okay, so we have another question from Flavia. Thank you for asking that question. The question is, how do you evaluate the possibilities of integrating these intelligent models with risk management processes? So we're just, tapping into that opportunity right now. And, we've only seen tens of projects really using that. I showed you many components, the mapping capability, showing you what is there versus what should be there, and comparing them. But that risk module, I played the video for you if you remember. I'm going to repeat that one more time. We've only done that and seen that in tens of projects, because it does require a lot of components on the part of the company to adopt. What we do here is different from Monte Carlo simulation, as I showed you in the formulation. So we try to learn the actual patterns of production and productivity and map that in the future. Oftentimes, people contrast it against the frac nets that you're using P6 for managing risk. They also want to see that's in the context of PERT or probabilistic scheduling, however you're formulating it. There's a lot of things that can be done in this end. Software companies that are active in the scheduling space, including Oracle, are also very interested in this. We are exploring that. All I've shown you is what we've already published and are publicly available for use. But beyond that, it is more at the research level at this stage. Thanks for the question. Taking into account RM is a transversal process and it crosses different processes. I'm not sure if I'm really following the question, Eduardo. Can you please help me with elaborating more on the question?
I'm also not sure, but I think she's interested in how about this, the risk management and project management, how those concepts are interrelated, if they are complex, the relation between project management and risk management, I guess.
Let me share with you one perspective that at least was, a new way of thinking about this. I had the opportunity working for a construction company here when I was practicing, Turner Construction. Turner is the largest construction management company in the US. When I came up with this concept and I worked with them, one of the feedback that was really fascinating to me was that, a large company like Turner has regional BDC managers, and all they do is they are engaging MEP coordination, pre-construction assessment. So they see BDC as one bucket of work. And they have also regional managers that are only focused on lean. So they've completely decoupled proactive project management, theories and practices that we have against the model-driven practices that we desire to see. And one great observation that I had coming from Turner to me was that we want to see if we can establish the synergy between the two. We want to see if our teams can start talking to one another because we see that opportunity. Now, dialing it in terms of academic work, yes, there's quite a lot of great work. I want to name a few of our colleagues. I apologize if I'm not naming everyone. Raphael Sachs has actually really tremendous amount of work on this area, a concept called Con-BIM that brings Kanban system and BIM together that enables some of these concepts. And there's a commercial solution that they also have in that space. Our colleagues at the University of Berkeley, California, Berkeley, they've also looked into some of these aspects of slowly introducing modules on BIM. I know some of the other colleagues in the UK and in Germany have also started looking into this. So we are all in early stages, but there's a desire at the industry level to minimize how resources are spread and bring synergy between these two decoupled areas.
Okay, our last question here.
Thank you for the question. The question is, are indoor point clouds integrated with outdoors? Yes and no. I say yes and no because really capture and mapping, there's not one solution that would fit all job sites. It depends. It depends on what kind of projects you're working on, what kind of capture mechanism you've decided to adopt. Are you using the 360 camera? Are you using the drone? Or do you want to use the two at the same time? So just to give you an example, and I'm going to show you one video on this question. We work with Pepper Construction in the state of Illinois, and owner on this project is really Oracle. And it's really fascinating because they fly drones every 2 weeks, one time, to sort of get a high-level view of the job site. But then they use a 360 camera, indoor and outdoor. And what they want to do is they want to integrate all of them together. So what we did is initially we mapped it with a drone, then we used the outdoor point cloud to bring that into automated alignment with indoors when the outdoor capture was actually connected with indoors. So the rest of the point cloud that was optimized against the outdoor point cloud was automatically aligned. Then there were so much changes that happened on the job site that visual data had a lot of disparity. So we used BIM through that manual process that I explained to bring that into alignment. So it's really a combination of automation and some user-assisted guidelines that can bring all this data. But this is, like I said, being practiced on hundreds of projects at a commercial grade. So we figure out workflows that can easily enable this with very simple interfaces. If you check the website for this platform, you can actually see quite a few demo videos on how this type of indoor and outdoor alignment can be done automatically and manually at the same time.
Moni, thank you very much. Superb presentation. I guess we have lots of comments from the audience congratulating you on the great presentation. Thank you, and we will continue with the conference for 2 days more, and I hope everybody can enjoy other great presentations. Thank you.
Thank you very much for the opportunity. Thanks for your attention today.
Bye-bye.